All right.
No, she didn't even break stride, bro. There was no time loss, okay? Kept going.
Whoa. It's clean in here today. What happened? Dr. Sprano's sick, you think? Really? Oh no. He didn't look sick yesterday. Uh-oh. Huh. Well, he should have. Well, interesting.
I gotta.
Dude, I know. You so confused. He was 22 minutes late. That's crazy.
All right.
I'm good, bro.
Sorry, I'm running late.
Oh, no problem. You're good. Take your time.
Actually, no, we have a lot to learn before. Yeah, no.
Hey, but if you procrastinate,
Not really.
then we don't have to accept
Really.
our procrastination.
You're pretty much done.
Are we gonna lack of understanding is the cause for hard issues then?
Pretty much.
Oh, that's great.
I mean, I have some more problems. There's some more problem types I'll work, but I would say that the tools that I've already showed you are pretty much sufficient to solve the problems. As far as I know. Well, I'll do a couple more things today that might help. All right, guys. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this morning. I thank you again for these students. Just ask you to just bless our work today, Lord. In your name I pray, Lord Jesus. Amen. Here's the, you can add imagine a column past the last one. There you go. Okay, so example. I'll start with this one. Suppose we want to solve, let's say, y prime prime, oh, I don't know. Let's see here. Plus, 3y equals to 0. Right. So I want to show you how we can solve this using power series methods. So the way to solve this with power series methods is pretty simple. You assume the answer is a power series, and then you plug it in. That's pretty much it. But then the devil's in the details, of course. So let's suppose we've got y is equal to sum n equals 0 to infinity of, let's say, a sub n times x to the power n, right? Then y prime will be the sum n equals 1 to infinity of n times a sub n x to the n minus 1. And y sub prime prime will be the sum n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2. There we go. Shouldn't bother us again. And so let me just make a forward-looking. So the thing is, we're going to plug the second derivative and put it equal to plus 3 times the first, plus 3 times y. We're going to set these equal to 0. So when we get to the stage of like combining them, it's going to be useful to like change the index. So let's do it on this one actually. So what I want to do is I want to let's say j equals to n minus 2. If I do that, then n is equal to j plus 2, right? And n minus 1 is j plus 1. And if I change the index like that, this becomes the summation j equals 0 to infinity. And my n is j plus 2. All right. And my n minus 1 is j plus 1. My a sub n is actually a sub what? A sub j plus 2. And then I finally have x to the power j. Now, all of this said, it's useful to switch the letter back to what we started. All right, so this is kind of a trick. Now, sometimes people don't even show you the step I just made. They just go straight to what I'm about to write. And I don't like that, because I think it's good to have an intermediate step where you can see what we did. But here's the next step. N equals 0 to infinity of n plus 2 times n plus 1 times a sub n plus 2 x to the n. So you say, well, wait a minute, but it looked like this with n. Why can it look like that with n? Well, understand that n and j, these are just dummy indices of summation. In other words, it's not about the letter, it's about the structure, right? So like there's a different pattern with this n versus that n, and these are equal. But you can do this. You can change the letter like this. And the reason I want to do that is because when I plug in what I just derived back into the differential equation, it's nice to have the same letter on both, all right? So what I'm going to do now, my next move, let me give this a name. Let me call this star, star, and I'll call the original one star. All right, so let's plug in. Let me get this unpleasantness out of the way. There we go. Plug in star and star star into y prime prime plus 3y equals to 0. And what do we get? Well, we get the sum n equals 0 to infinity, right? N plus 2 times n plus 1 times a sub n plus 2 x to the n plus the sum n equals 0 to infinity. I forgot something, right? What did I forget? I forgot the 3. So I'll put it there. Give me a second. All right, 3. I'll put it out here. 3. And then we can combine these, right? We've got actually the sum n equals 0 to infinity of what? N plus 2 times n plus 1 times a sub n plus 2 plus 3 a sub n, parentheses x to the power n, is equal to 0. So if there's a problem like this in your homework, and you should solve it the same way, essentially. You just guess the solution is a power series, plug it in, and then we work it out, make everything look the same so you can combine terms as much as you can, which looks like this here. Then what does this mean? In order for this to be equal to 0, we must choose the coefficients so that it makes the coefficients 0 order by order, right? In other words, I have to have, what I'm going to need from this, what I get is this. I get a sub n plus 2, right, has to be equal to minus 3 a sub n divided by n plus 2 times n plus 1. And that has to hold for n equals to 0 and 1 and 2 and 3 and so forth and so on all the way up. All right? How do you solve such? This is a recurrence relation, right? It's a whole sequence of recurrence relations. Or it's just one, it's just one recurrence relation. It's just one recurrence relation amounts to like infinitely many equations that are, kind of nicely related to one another. So we just start. So let's see here. What I'm going to do is I'm going to look at n equals to 0. N equals to 0, what do I get? I get a sub 2 is equal to minus 3 a sub 0 over 2 times 1, right? This is n equals to 2. So it's natural then to next to look at n equals to 4. N equals to 2, rather. Did I say this is n equals to 2? This is n equals to 0. Okay, so a sub 4 is equal to minus 3 a sub 2 divided by 4 times 3. All right? But what do we know about a sub 2? Right above it, right? We can simplify that. So what you got here is actually minus 3 squared times a sub 0 divided by 4 times 3 times 2, right? In other words, you've got minus 3, well, let's see here. You've got minus 1 to the power 2 times 3 to the, well, times 3 squared, a sub 0 divided by 4 factorial, apparently, right? Let's see here. N equals to 4. What happens? We have a sub 6 is minus 3 times a sub 4 divided by 6 times 5. All right? Then what happens here? Well, we know what a sub 4 is, right? So we can plug that in, and we have minus 3, in this case, cubed times a sub 0 over 6 times 5 times 4 factorial. In other words, you could write this minus 1 to the third power times 3 to the third power a sub 0 divided by, well, 6 factorial. Do you start to see the pattern? Maybe? Maybe not. I don't know. But if you look at this, tilt your head and squint, you can see that a sub 2k, right, is actually going to be equal to what? Yeah, let's see this. Let me just some fine print here. This is k equals to 0. This is k equals to 1. This is k equals to 2, right? If n equals to 2k. So we have, what did you tell me? Minus 1 of the what?
Minus 1 to the k.
Uh-huh.
3 to the k.
Uh-huh.
A2 for a.
A sub 0, right?
Correct.
Divided by,
K plus 2 factorial.
how about, huh? What? I'm an idiot. Is this k equals 0? No. Wait a minute. I'm a dummy. Listen, so I'm getting confused about the distinction between n plus 2 versus n, okay? So I have labeled this over here. The n is, I'm labeling the n here in these labels, right? On the left-hand side, we have n plus 2, right? So like this is n plus 2 equals to 2, right? So n actually equals to, n equals 0, but sorry. Yes. Anyway, so you guys don't care. I'm the only one that's confused at the moment, right? Let's see here, k equals 0. So I was,
K plus 1, K plus 1.
my point is I should be looking at these here, right? For the pattern. Because that's a sub 4. So you notice there's a 4 factorial here. There's a 6 factorial here. So if we have 2k, we put 2k factorial here.
Yeah, shouldn't it be k plus 1?
No. The pattern is this. This 2 matches that 2 factorial. This 4 factorial. This 4 matches that 4 factorial. This 6 matches that 6 factorial. So. Oh, you think I'm missing a...
Isn't it start at k equals 1?
Let me erase this. This is not helpful. So this is k equals to, this is k equals to 1. This is k equals to 2. This is k equals to 3. All right? Because n equals to 2k. So 2 times 1 is this one. That's why there's a minus here, minus 1 to the k. 4 is 2 times 2. That's where there's a minus 1 squared here, because 2 to the minus 1 to the 2 is 1. So we're right. I just mislabeled the k's in my. I was trying to be helpful, and I was hurtful. Okay, so. All right. Yeah.
With that, how did you get the ace?
What do you mean? It's everywhere.
I mean, how do you define that in
Oh, what is, okay, that's a good question. This is for n equals to 0, 1, 2, 3, right? So you can't ask me the question, what happens when you put this n equal to 0? You can't do that. That would put this to minus 2. That's not even part of the story. Our recurrence relation starts at 0 as it's situated. In the larger story of these kinds of problems, it's a lot of times the case that you have to look at the first couple cases separately. And the pattern only picks up after like one or two indices. But probably not for the problems I assigned you guys this semester. The one I've assigned you guys in the homework is very similar to this, actually easier. So, okay, so how about, what else is there? Well, there's the odd indices, right? So what if we look at n equals to 1? So that gives us information about a sub 3, right? I'm saying about n equals to 1 in this equation here. That's the n I'm referring to, all right? So n equals to 1 in that equation, I get a sub 3 is equal to minus 3 a sub 1 divided by what? Well, 3 times 2. And then if I look at n equals to 3 in that equation, I get a sub 5 is minus 3 times a sub 3 over 5 times 4, which is minus 3 squared times a sub 1 over 5 factorial. And if I look at n equals to 5, I get a sub 7 is equal to minus 3 a sub 5 over 7 times 6 times, that was times 3 factorial. Excuse me, though, my bad. That's fine. And that, when I plug in what a sub 5 is, I get minus 3 cubed a sub 1 over, 7 times 6 times 5 factorial. But that's exactly, well, I've run out of board, sorry. That's 7 factorial, right? My point is, the pattern is very, very much the same for the odd indices. And you can readily see, if you don't get confused like we got last time, that a sub 2k plus 1 is straight up equal to minus 1 to the k times 3 to the power k times a sub 1 divided by 2k plus 1 factorial. So it turns out we guessed an answer with infinitely many parameters, right? We had a sub 0, a sub 1, a sub 2, a sub 3, I mean all the way on out, right? And what has happened is that we only needed 2 arbitrary constants in our solution, right? Everything can be written in terms of a sub 0 or a sub 1. So let's write it out then. What do we have? What's our solution? So we've got y is the sum, right? N equals 0 to infinity of a sub n times x to the power n. But how does that work? Well, if you don't mind, I'm just going to skip one step. I'm going to pull the a sub 0 out of the first sum. And so here's the even terms. K equals 0 to infinity, apparently minus 1 to the k, 3 to the k divided by 2k factorial, x to the power 2k. So all I did there, guys, is note that there is an a sub 0 in every single even term, so I can factor the a sub 0 out of that series. All right? Are you guys with me? And we can do the same with the odd ones. I can pull the a sub 1 out because it's on every single coefficient here, so I can factor it out. And, excuse me, what do you got? What are these functions that we're looking at? Can you recognize them? Maybe not. Let me rewrite them just a little bit. What's that?
Sine and cosine.
They're sine and cosine. They're almost sine and cosine, right? But there, you see, it's not quite right, right? Because, for example, cosine of theta should be the sum k equals 0 to infinity, right? Minus 1 to the k divided by 2k factorial, theta to the 2k. But that's not the pattern we have, right? Our theta to the 2k, it seems like it's equal to what? Yeah, 3 to the k times x to the 2k, right? So what I heard somebody say a magic word. Who was that? Somebody spoke the word square root. Yeah, very good. So you can take this and turn it into a what? 3 is, this blows my college algebra class's mind, but I do this sometimes. I'm like, see? There's a square root of 3 there. You just have to just look at it, right? They don't like this. But you do need to do this in places. And this is such a place. See, that is the square root of 3 times x to the power 2k. Because if you undo that, you have x to the 2k times square root of 3 to the 2k, which is 3 to the k by laws of exponents. So this is actually what? A sub 0 sum k equals 0 to infinity minus 1 to the power k times parentheses square root of 3x to the 2k divided by 2k factorial. Now, technically speaking, if you just want an answer, right? The thing I just wrote before what I'm writing right now was already an answer, right? It's a power series solution of this given differential equation. But if you'd like to put your answer in terms of happy-go-lucky functions that you already know about, then this is what you got to do. Because this allows you to see that you're actually looking at what? A sub 0 times the cosine of what? This is actually a sub 0 cosine of the square root of 3x plus a sub 1 times the sine of the square root of 3x. And once you find that, it's really easy to go back to the original problem and check it. Think about that. If you differentiate that 2 times, what happens? Think about differentiating that twice. What happens? Uh-oh. The camera seems to have followed me. Wait a minute, did we ever move the camera?
Nope.
Oh, man. Son of a gun. Oh, no. Austin, see, this is what happens. Well, I guess the good news is all the hurtful things I wrote in the middle board I just talked about, but they didn't see, so. Sorry to all the Austins who aren't here right now. I think we're missing both of our Austins, actually. Well, hopefully that's long enough for Austin to see it. Over here is the other thing I wrote. So think about this, right? If you differentiate our answer twice, what happens? Cosine goes to sine, right? Excuse me, cosine goes to minus sine, and sine goes to cosine for the first derivative. What happens in the second derivative? If you think about 2 derivatives of sine and cosine, it goes back to minus what it started with, right? But the chain rule does what? It pulls out a square root of 3 each time. So you get minus 3. Basically, you can easily see that if you differentiate this function 2 times, you get minus 3 times this function. That's just a fancy way of saying it solves this differential equation, right? Because if you differentiate y twice, you get back minus 3y. So when you plug that into here, it works. So why are there 2 constants here? Yeah. Right. It's a second order differential equation. So intuitively speaking, you can think about this in terms of physics if you like. If we had x as time instead, then what we're saying is this is the position as a function of time. And in order to specify the position as a function of time, you need an initial velocity and an initial position to fix the solution. So this is the nature of a second order differential equation. In the general solution, there will be 2 parameters. The problems we mostly solved earlier in this course were first order differential equations, right? So we just had 1 constant in them. But we did solve an equation. We did solve a differential equation like this, right? by making reduction of order, and then we did an arc sine integral. This is an easier method to solve that problem, I would argue. I don't know, it's kind of on the bubble in terms of easiness. This becomes easier if what happens? If this 3 is not present, this problem becomes easier, right? That's your homework problem. So, yeah.
So the underline is the answer, not it.
Yeah, the underline, I would say the underline is the best answer here. Yeah. This one is, I'll tell you. I saw your question, Andrew. I'm just trying to. So I basically just solved problem 114 for you, although, oh man, 114's got some more data. 114 actually even gets, so here's the thing. Problem 114, I tell you the value of y of 0 and the value of y prime of 0. So you got two different paths you can go down. The one path you can go down is do like I just did here, find the general solution, and then at the end of all that, apply the initial conditions to find specific numbers for the a sub 0 and the a sub 1 in the solution. The other path you can go, so like I think in that, I don't know, so it's even easier, in some sense it's even easier if you apply the initial conditions at the start. So like in problem 114, you have y of 0 is 0. And y prime of 0 is equal to 1, right? So this is problem 114. Let's just think about this problem. What if I gave you that? What if I gave you those initial conditions? How could have our life been different here? What do the initial conditions tell you? So think about this. If we have y is the sum, right? N equals 0 to infinity of a sub n x to the n, right? You can also notice that that's the sum, n equals 0 to infinity, right, of the nth derivative of y evaluated at 0 over n factorial times x to the n. This is Taylor's theorem, right? So what does this tell us? This tells us, this immediately tells me that 0 is equal to, and by the way, this is y of 0 plus y prime of 0 times x plus 1/2 y prime of 0 times x squared plus da 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 da. That's all the notation above means. All right? So if you look at that, we have the initial conditions y of 0 is 0, so that means what? A sub 0 is 0, right? And a sub 1 is just 1. So basically, if you impose those initial conditions at the start of your calculation, half of this calculation goes away. Because for the even terms, you just go, well, you know, clearly the even terms are linked to a sub 0, right? So the fact that a sub 0 is 0 makes a sub 2 is 0. The fact that a sub 2 is 0 makes a sub 4 equal to 0, and so forth and so on down the chain. So all of the even terms die. And all of the odd terms, every place I've written a sub 1, that becomes 1. It's not, I don't know, it's like, it's really the same calculation. It depends on which way you want to go. So you could use that to do your problem 114. I don't know, I'm kind of ambivalent, which is better. Okay, you guys have a question about the homework. I've got that out of my system, yeah.
Other question, what was the purpose of making n equal to 2k?
Oh, just the pattern. So if we want to talk about even numbers, it's useful to index n in terms of twice another number.
So it'll only be even.
So yeah, this is just our go-to formula for even numbers. N equals 2k.
2k plus 1
Two.
will always be odd.
2k plus 1 for odd, right? Yeah.
So why'd you use the 2k to find, why'd you use the n plus 2 instead of 2k to find like an a3, a5, and a7?
Why did I use the, wait a minute, what?
You plugged in 1 to find like a of 3. Why didn't you use the 2 n equals 2k? You used the a n plus 2. I'm worrying this terribly, I know, I'm sorry.
Well, it's because I mean, ultimately, I'm interested in the formula for, okay, so like this formula puts n plus 2 over here. That's just how it is.
Okay.
However, at the end of the day, I'm interested in the formula for a sub 2k. So that's why there's a distinction. I mean, I guess if you want me to apply it directly to here, maybe I should say n plus 2 equals to 2k, right? That's probably the missing link here. Right? Other questions? Yeah.
Can you do an example where you represent Taylor series expansion rather than just in terms of the Taylor series?
Can I do what, just say it again?
Can you do an example where you represent a Taylor series expansion rather than the terms of the Taylor series? So like the representation is the sum of x of those things.
I don't know what you mean.
So instead of doing a Taylor series function, you just ignite the derivative.
Oh, one where we actually just differentiate and work it out?
Yeah, instead
Yeah.
of expanding it to a sum.
Well, I don't think that's interesting. I mean, what I'm saying is I don't know an example where that's interesting. Right off the top of my head, I have to think about it. Let me think about that for a second while I'm erasing. I mean, 90, the lion's share of examples that I can think of, they all involve using, you know, about 5 examples that we know: geometric, sine, cosine, exponential, cosh, and a substitution paired with either multiplication or division of series and these kinds of techniques. It is rarely the case that, I know one. I know one. Here's one we don't have anything for. We almost have to do it. Example 2. Is there a particular problem in the homework you're thinking about, or your question is just in the wild?
I think there's several in that one. For instance,
110 and 111? I mean, I still need to do the, I should still do, these. Okay. These are geometric series problems. Yes. So I'm glad okay, so first of all, let me just say this. I do think your original question is not unwarranted. So problem 109, I tell you, use the geometric series technique, right? So you can't miss that one. I mean, you can miss it, but the instructions are there, right? Problem 110, I don't say what to do. However, the smart thing to do there is to use the geometric series technique, or perhaps to even just use what we already know, which is the series expansion for the log of 1 plus x. Right? So for like problem 110, here's how I'd go. So for problem 110, you've got the log of, 1 plus x over 1 minus x, right? So properties of natural log, this is the log of 1 plus x minus the log of 1 minus x, right? But hey, we know the Maclaurin series for the log of 1 plus something. So use it and make a substitution for the second one, because it's the log of 1 minus something. So can you guys tell me? What was the log of 1 plus something? It was what? It was the sum. I think it was sum n equals 0 to infinity. Golly. I think it was 1 over n plus 1, x to the n plus 1, maybe? Negative 1 to the n?
Yeah.
Right. I always check it against the natural log of 2 because I remember that. Like the natural log of 2 is the alternating p equals 1 series. And that's what happens if you plug x equals 1 into this, right? So that checks what you guys told me. And then what is this? Minus 1 to the n, right? Over n plus 1 times what? Minus x to the n plus 1, right? And that as well. Thank you. Now, I haven't done any ones quite like this. This is actually kind of an important calculational discussion. So what do you got here? Oh man, if I write too much more, I'm going to solve it. I'd be careful. Minus 1 to the n over n plus 1. Maybe there's more to it than that, though. X to the n plus 1. And then what happens over here? Minus the sum, n equals 0 to infinity. What we got? We've got this minus and this minus, well, excuse me, minus 1, I'll write it out. Minus 1 to the n, minus 1 to the n plus 1, divided by n plus 1, times x to the n plus 1, right? So what's the situation there? What is minus 1 to the n times minus 1 to the n plus 1? It's negative 1, right? So these two guys, you get minus 1, I'll write it out. Minus 1 to the n times minus 1 to the n plus 1 gives me minus 1 to the 2n plus 1. But minus 1 to the 2n is just 1. So that's just minus 1. So that's the coefficient, right? But there's a minus outside. That minus and this minus gives you a plus, right? So what you get the sum, n equals 0 to infinity. Ah, man, that's supposed to be infinity, sorry. Minus 1 to the n plus 1 divided by n plus 1 times x to the n plus 1. Now, that's a potential answer for this homework problem, right? But it's not the best answer because it's not simplified. How would you simplify this? Yeah.
The odd powers don't exist.
The odd powers don't exist. I agree. Yeah, so if n is odd, you get minus 1 plus 1, which is otherwise known as 0. And so 0 does not exist. But, well.
That word.
No, you're fine, you're fine. 0 is dead to us. We're going to work with the new number system. 0 will not be a real number anymore. It's fine. No, but that's exactly it. Exactly the point is you should split your analysis into even and odd, right? So you can take any sum over all the integers and you can split it into the sum over the evens and the sum over the odds. The odds are 0, all the coefficients. So in other words, you can rewrite this as the sum k equals 0 to infinity, right? Of what? 2 over 2k plus 1 x to the 2k plus 1 apparently. N equals to 2k. And by what we were just talking about, if you also wrote down the sum over the odds, well, all those are 0. So they don't. I seem to have solved this homework problem. I'm sorry.
No.
You forgive me? Yes? Okay.
Never.
So that's problem 110. Problem 111. Again, I think geometric series are the way to do this, but you have to be a little bit creative. All right, so I have f of x. I will not solve this I will not finish this problem. I'm just going to give you a hint, okay? 1 over x. I'm not good at giving hints. I have this proclivity for solving the whole stupid problem. It's hard for me to give up on like halfway of the solution, you know? But we're supposed to find the Taylor series expansion for this guy centered at x not equals to a for a not equal to 0. So what you want to do basically is just this. You know, you have to imagine that is really just x minus a plus a, like that. And then you're trying to expand it in powers of x minus a, right? So the next thing you do, well, actually, I'm not going to do anymore. What you want to do past that is try to preserve this, right? You want to keep that in some fashion or form, and you also know what the geometric series says. What c over what 1 minus r is c plus cr plus so forth, cr squared, and so forth and so on, right? So if you can make this become that pattern, then you can use the geometric series. What would you guys suggest we do? Factor what out? What's that? Factor an A out, right. Factor A out. And then you'll be able to see how to use the geometric series. So this is very similar to a problem I did in class before. But I think it was like 1 over 1 minus x that I started with, but the principle remains the same. Problem 112, again, yep. Well, this one is not geometric series. This one I would say use the like adding angles formula and the known Maclaurin series for this one. So for problem 112, it's kind of the same hint as problem 11 though. Problem 112. Although you could just straight use Taylor's series if you wanted there. What was this? You guys have to remind me. F of x equal to what? Sine of pi x, and I said x not equal to what? 1. So what to do here? I think I did this before, but you guys probably forgot because it's been a little bit. This is sine of x minus 1 plus 1, right? So this makes that sine of pi times x minus 1 plus pi. So then you can use the trigonometric identities to convert it to sines and cosines, and then use the Maclaurin series to find the expansion. Well, you can use the substitution into the Maclaurin series, right? You're going to substitute, basically you're going to substitute u equals to pi times x minus 1 into the known Maclaurin series. So this is why I was reacting to your question as I did. It's because most of the homework I've given you doesn't have to be solved by direct application of Taylor's theorem. And while you can pretty much do that for any problem, it's almost always the wrong way. An exception to this that I know of is inverse functions. I don't have anything nice for inverse functions. For example, if I had f of x equal to inverse hyperbolic sine of x, and I wanted to find the first few terms in the Taylor expansion for the Maclaurin expansion for this, that's not 1 over sinh. I can't use long division, okay? So we don't have a method for this. Although there is something sneaky you could do here. Let's see if you can figure it out. Differentiate once. And so you guys remember the derivative with respect to x of inverse hyperbolic sine is 1 over the square root of 1 plus x squared. Everybody remembers, right? Yes. So it's about 70% of you don't know this. And that's okay. But you should be able to derive it, right? I won't do that at the moment, but you can derive this. So then what? Oh, look at that. What's this? This is a binomial series, right? I mean, this is 1 plus x squared to the minus 1/2, is it not? So I can look at that as, 1 plus alpha u plus 1/2 alpha times alpha minus 1 u squared plus dot 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 dot. See, if I just want the first 3 terms, I can get them, right? And I don't have to because do you want to differentiate this again? No. So you see, I always do anything I can to avoid further. I don't know. Maybe it's easier just to differentiate again. But here's the first 3 terms without too much work. And so alpha is minus 1/2. And so what you've got is what? 1 minus 1/2 x squared. So what's minus 1/2 minus 3/2? So that's a plus, right? 3/4, but that's 3/8, I think. Plus 3/8. U squared is, here u is equal to x squared, right? So x to the 4th plus dot 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 dot. Now is that the power series for the function? It's not. It's the power series for the derivative. So how do we get back to the function? We integrate. So f of x equals 2. A constant plus x minus 1/6 x cubed plus 3 over 40 x to the 5th plus dot 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 dot. How do I figure out that constant? Well, I plug in 0. But the inverse hyperbolic sine of 0 is 0, and that series evaluates to c at 0. So in short, if you'll forgive me not writing more, this constant is actually equal to 0. And so there you go. This is the Maclaurin expansion for inverse hyperbolic sine to 5th order. To calculate this directly from Taylor's theorem, I would have to differentiate inverse hyperbolic sine 5 times, which would not be pleasant. And you see, I could easily generate further terms by just keep going in the binomial series. So this is a useful trick. But there are other functions that, when you differentiate, it doesn't come to something nice. I mean, this is still a special example. Yeah.
On P112, why can't you just put pi x as your u, plug it into the Maclaurin series?
Because we're asked to find the expansion centered at about 1.
Oh, okay.
So that's the issue. We're looking for powers of x minus 1. Yeah. Uh-huh.
So when you're trying to find it centered at 1, why would you use like -1 + 1?
Because that makes an x minus 1 appear. I mean, to find an expansion centered at 1 means you're looking for an expression of the form, sometimes some coefficients, let's say c sub n, times x minus 1 to the n power, right? So how do I make x minus 1 appear where it's not? Well, I add and subtract 1. That's my trick anyway.
So, I mean, it really doesn't do anything, but it does at the same time because, like, -1 + 1 is 0.
What it does is it makes x minus 1 appear explicitly, right? You're just writing the function in terms of what you want. So that puts you one step closer to the answer. Because you want to find it expanded in powers of x minus 1. That's the idea. Let's see here. All right, I should go back and, although, one of the things we haven't done yet is there's another application, all right? So like I've showed you, we can use power series to solve all kinds of differential equations, right? We can do integrals that we couldn't do before also, right? Oh, thank you. Pity on me. But we can also solve limits. There are limits which you just don't want to do without power series. There's a whole bunch of limits that become way, way easier with power series. Let me show you some like very, very rudimentary examples of that. How about this? Here's one we've known about for a while. The limit as x goes to 0 of sine of x over x. So this is the limit as x goes to 0 of, what's the power series for sine? X minus 1/6 x cubed plus dot 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 dot, right? Divide by x. How do you divide by x? That one I don't need to teach you long division for, right? That one you can just do. It's 1 minus 1/6 x squared. The next term is plus 1 over 120 x to the 4th, and so on and so forth. What's that limit? It's 1, right? So did we need to apply L'Hopital's rule? Oh, we did not. Did we need to look at, I mean, the way it's derived is geometrically to start with. And the truth of the matter is to take the derivative. All right, so here's another one. If I can get this out here. I need to, my phone is fuzzy. How about the limit as x goes to 0 of the square root of 1 plus x minus 1 minus 1/2 x divided by x squared. First of all, it's indeterminate, right? If you plug in 0, you get 1 minus 1 upstairs, which is 0. All right? So I've assigned you in the last part of the homework problems from Stewart. This is one of the problems that's right next to one of the problems you're assigned, okay? And the method that you use to solve the problems that I've assigned is the same as what I'm showing you now. You just convert the given functions to their Maclaurin series. And then you simplify. It becomes obvious what the limit is through just algebra. This guy we can do what? This is binomial series, right? Alpha equals to a half. So this is literally 1 plus 1/2 x, right? Minus, I want to say 3/8 of it? X squared. I think I just did that, didn't I? Oh, wait a minute, but that was reciprocal, wasn't it? Alpha's 1/2, so I do 1/2, and then 1/2 times 1/2 times minus 1/2. I think that's a minus 1/8. I should have minus 1/8, right? I didn't do it wrong. Let me work it out. 1/2 times alpha minus 1. What is that? This is the mistake I always make on these stupid problems, is I forget to actually do the arithmetic. So alpha is a half here, right? So 1/2 times 1/2 times 1/2 minus 1 is negative 1 over 1/2, right? So that's minus 1/8. So, oh, okay, yeah. And then we have what? Minus 1 minus 1/2 x. So what happens? And of course, there's the plus dot dot dot, right? Let me not neglect the plus dot dot dot. Maybe I could put the plus dot 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 at the end. The point is that what you've got is the limit as x goes to 0 of minus 1/8 x squared plus higher order things, right? Plus like some constant, let me just say k. What's the next thing? X cubed, right? I don't care what that constant is, so just write it like that, okay? I mean, you could figure it out. It's whatever 1 over 3 factorial times alpha minus 1 times alpha minus 2 is, but I don't care. The point is it's a number, and that is x cubed. We divide by x squared, what do we got? Minus 1/8, right? Plus some constant I don't know, but I don't care. And then x, rather, right? Plus higher order stuff. Now all of this in the limit goes to 0, right? Here. This is what the arrow notation was invented for. So this stuff all goes to 0. And the answer is 1/8, yeah. So the way to solve these limit problems is to figure out the appropriate power series expansion for the functions you're looking at. And by doing that, you'll be able to reduce the problem by algebra of series. So this is a really important trick to know about for calculating difficult limits. Yes, sir?
Can you just make the rest of the terms in that equal to k? Is that what you did on that?
Well, my point is, first of all, the k is literally 1 over 3 factorial times 1/2 times minus 1/2 times minus 3/2, whatever that is, who cares? The bigger point is there's an x here. So as x goes to 0, that goes to 0. And past that, there's an x squared and an x cubed and so forth. All those terms vanish, and we're just left with a constant.
Oh, so the 1's canceled out and the negative 1 has. Okay.
Yeah, yeah. And then so here I'm just dividing by, when we divide a series by a power, by just a simple term, then we just drop the power each by 2. Let me see if I can find another one. Yeah.
Just to be clear, the square root of 1 plus actually the divided series.
Yes, that's binomial series. Yeah, I'm using binomial series. So the square root of 1 plus x is 1 plus x to the 1/2 power. And so that's the binomial series if you want to expand it. Or we could take derivatives and plug in 0 and yeah.
Where did the x cubed come from?
Where did the x cubed come from? That's the next thing in the binomial series. It's 1 plus alpha x plus 1/2 alpha times alpha minus 1 x squared plus 1 over 3 factorial alpha times alpha minus 1 times alpha minus 2, x cubed, and so forth and so on. So it was that, just that there. Mm-hmm. See if I can find another one of these. Let's see here. Oh man, look at that. It's a mess. Well, actually, before I do another example, is this method clear? Or I think we should do other problems, actually. Yeah. I can do more, but do you guys get the idea? This is basically the theme of this part of the course is you can take pretty much any problem that you come up against in calculus, and if you replace the function with the power series equivalent, all of a sudden you've changed the problem from one that you may or may not be able to solve to one that is essentially a problem in polynomials with some fine print, right? You might have to keep going to resolve your issue, but essentially it reduces non-polynomial problems to polynomial problems. That's the beauty of it.
So all we need to know for the final is the power series.
It wouldn't hurt. I mean, that's a good chunk of it. Yeah. Let's see here. Now I do have this. Well, let me work something that's like problem 115, but not quite the same. So, example. What am I? Example. 5. Yeah, thanks. So what if I was up against the solution of, say, e to the, I don't know, x cubed divided by y. And I know that y of 0 is equal to -1. So how should I solve this? Worlds are colliding, so we have to think back to the other part of the course, right? How do we solve this kind of differential equation? What do we do? Yeah, separation of variables carefully. Combining both of your answers. Let's hear y dy is equal to e to the x cubed dx, right? Separate, integrate. But how about integral of e to the x cubed? Can you do that? Without power series? Like I can't without power series. Now the left-hand side is easy enough, right? 1/2 y squared, right? And so we're going to have equals to the what? The integral of the sum, right? N equals 0 to infinity of 1 over n factorial, yeah? X to the what? X to the, so we have x cubed to the n, right? So we don't do x to the n, we do x to the 3n for this one, dx. But you can do that. So you got what? Sum, well, we add a constant, don't we? So constant plus the sum, n equals 0 to infinity, 1 over n factorial times, in my case, 3n plus 1, x to the power 3n plus 1. It's not quite the Larry, Moe, or Curly function, but looks kind of like it. Not really, though. And then we can do what? We can say, okay, well, that means that y is equal to plus or minus the square root of c plus, well, 2c. Fine. We don't have to call it 2c, right? We can call it c bar or k. I'll take it. Okay, k plus. Now, when I multiply the two, it does multiply.